Hello and welcome. In this video session, we will discuss the exec system call. The exec system call is a function which is used to load a new program in the process memory. So there arises some use cases in which the current program needs to be discarded and the new program needs to be loaded in the memory. So this exec system call is used to perform such operations. The process, stack, data and the heap are replaced by the new program, and the new program starts its execution from the main function. Let's see the syntax of the exec system call. The exec system call takes three parameters: the path name, the argv and the envp parameter. So the exec system call, on error it returns a -1, but upon success it does not return anything. So let's see why it does not return anything. And also for more reference on exec system call, we can see the manual pages of the exec. Let's have a look into the manual pages of exec. So we can type man space 2 space followed by the exec. So here we can see the syntax as well. It includes the file name, the argv and the envp, and we have to include the unistd.h. Let's see the example to understand how this exec works. Also, there is a set of library functions called as exec family function calls. There are some variations of exec library functions which is implemented on top of the exec system call. So exec is a system call, and all this are library functions which are implemented on top of the exec, and these are also used to replace the existing program memory with a new program. And similar to the exec, these library functions returns a -1 on error, and in case of a success it does not return anything. Let's see a few of the examples of this exec family library functions and exec system call in order to understand how the exec works. Now let's see an example of exec library function. So in this window we have two programs, p1.c. The lower half has a p1.c and the upper half has p2.c program. So here each program has a main function, and in p1.c we have a print saying that the process we are printing the process ID, and then the p1.c calls an execl and passes the location of program 2's binary file and gives R1, R2 and R3 as command line arguments for P2 program, and the P2 program prints the process ID and it mentions that this is a program called from execl, and then it prints the arguments, command line arguments. Let's compile this program and see the output in order to understand the execl function call. Let's compile the program. We have compiled the p1.c. Let's compile p2.c. So here the point is p1.c is a separate program and p2.c is a separate program, and p1.c is calling p2 from using the execl function call. Now let's execute p1. So after executing p1, let's analyze the output. We are getting I am main process PID equal to 6616. So this is coming from the first program from this line, and we have got the process ID as 6616. Then after this, the program 1 has executed execl. By executing the execl, the first program virtual memory is replaced by the second program's virtual memory. So after this, we can see the output. I am a new program called by execl. So this output is coming from the second program from this line. Then if you see the command line arguments here, argv0, argv1, argv2 corresponds to the argument that is passed from program 1, and we have to pass a null here from the program 1 execl. So by this we can also, a point to be noted is this line from the program 1 is not printed. If you see the output here, we don't have any line corresponding to this print here. This means the program wants virtual memory that compromises of text, stack, heap is completely replaced by the program 2's virtual memory, which is the stack, text and data memory. So execl here replaces the existing program by the new program, but it remains under the same process. Hello and welcome. In this video session, we will see some examples of execv and execve functions. Let's begin with execve function. We have two programs in this folder, program p1.c and p2.c. Let's open individual programs. So this is the first program p1.c, and let's open the second program. So we have two programs here. The upper half is p2.c and the lower half is p1.c. As you can see here, from p1.c we are calling the execve function. This is a library function, and here we are calling the executable of program 2, and then we are passing the arguments. So here arguments is an array of char star. So args contains the arguments that can be passed on to the p2 program. And here, if you see, this line will not be printed when we execute the p1. This is because the execve replaces the current program virtual memory with the new program's virtual memory, and once the p2 is being loaded on the memory, this program runs and it begins its execution from the main, and it prints this line, and then it prints the argument. So this argument will be from the argument passed from the p1.c. So here the argv holds these arguments, and as a note, we should always end this arguments with a null. So let's compile individual .c files and then execute it. So as a note, p2 should be compiled and stored as p2. So now let's compile each .c files. p1.c -o p1. In the same way, let's compile p2.c and let's name it as p2. So here p2.c is compiled as p2. This is because from the p1.c we are calling p2 as the object file of p2. Now first, if you run p2 separately, let's run p2 separately. So if you see, we have got some arguments here. We can see, let's pass some arguments. Test1, test2. So here, this is arg0, arg1, arg2 for p2 program. Okay, so we have arg0, arg1, arg2 for p2 program. So now if the same thing if we run via p1, so if you see here, the main program p1.c is run using this. We got this p1.c. Then I am a new program called by execve. So we got this line. This is because it has called p1 has called execve, and the virtual memory of p1 is being replaced by p2. Hence we got this line as a print from p2. And if you note here, argv of 0, argv of 1 and argv of 2, these are the parameters that has been passed from the p1 program, r1, r2 and r3 followed by null. So this line is not printed here. So you see, this line is not printed. This is what we had discussed in the previous video session, that if execve is success, then it doesn't return. If it fails, then it returns -1. Now let's see next set of examples. As a note before this, if you want more information on this, we have to type man execve. So execve manual pages are here. This is the execve function syntax. It takes the path of the new program and the arguments basically, and we need to include the unistd.h as required. Now we will see example of execve system call. Now let's open the first program, program1.c, and let's open the second program as well. Let's open it within the same window. So now we have two programs. The top is the program2 and the bottom of is the program1.c. So in this case, execve is the system call which is used here, and as a note, on top of execve, the other library functions such as execl, execv are implemented. So the main use of execve is we can change the environment of the second program. So in this case, let's have a look how it works. So the execve calls the required parameter for program 2, and then it also sets some argument variable and the environment variable. So here env is the character array which holds character pointer. This is basically an array to character pointer, and similarly argvec is an array to character pointers. So we pass argvec as the second parameter, which is nothing but this arguments, and then envvec, which is an environment vector, and we pass it as the third parameter. As a note, we should always have a null in the end. So now argv of 1 is the program 2's object file that we are passing. So we need to pass our program 2's object file as a part of the argument argv for program 1. And once the program 2 is called here, we have this program in memory. So the program 1 virtual memory will be replaced by this program 2's virtual memory, and we get executing program 2. And here we print the argument. This argument here will correspond to this here. Welcome to LSP will be the argument which we pass, and it will be passed here. And then the environment we print here. So the environment here will correspond to the environment that we pass here. So one of the main use case of execve is when we have to work with the environment variables, or when we have to pass new environment variables to the new program, then we can use it. Let's have a demo on this. Let's compile this and run and see the output to understand better. Let's compile each of the programs separately. GCC program 1.c minus object file GCC program 1. So in the same way, let's compile program 2.c. Now we have compiled both the programs. Let's say we run program 2 first and see what is the output. And let's pass some parameter, param1, param2. Let's see the output. So if you see here, what is happening is the param1 and param2 are taken as the parameter here. So argv of 0 will be this one, argv of 1 is this param1, argv of 2 is nothing but this one. So if we execute program 2 initially, this is the output. So the program 2 has its own environment variables. This is discussed in one of the previous video session. Now this corresponds to this program. So we are printing the argv in a loop that we have passed here, and we are printing the environment variable here. So this prints the environment variable. We have a extern environ which can be used, and we can print the environment. So this prints the environment in this format, the value and the key format. So now if we run the same program using program 1, let's run this using program 1 and pass program 2 as the argv of 1 points to the path where program 2 object file is stored here. So if we pass this, let's see the output. Now if we run this, the environment variable of program 2 is being replaced by the environment what we have passed in the program 1 here. So the new environment of program 2 will be this what we have passed. All the old environment of the program 2 is being replaced by the new environment that is being passed from the program 1, and these are the command line arguments that is passed to program 2 via program 1. So this is the command line arguments. Okay, so let's have a small look on the manual pages of this as well. So let's go here. In order to open the manual page of execve, we have to type man space 2 space execve. So we get this here, execve. So unistd.h needs to be included, and this is the path of the second program object file where in which it will be replaced by the program one's virtual memory will be replaced by this new program, and this is the argument command line argument for the new program, and this is the environment list of the new program. So this is what we have used here. In this video session, we will discuss on the combination usage of fork and exec. So in the previous video sessions, we had discussed fork separately and exec separately. So fork is a system call used to create a child process, whereas exec family of function calls are the one which replaces the existing program virtual memory by the new program's virtual memory. Now let's see how the combination of fork and exec actually works. And in most of the use cases, exec is usually used along with the fork. So let's go to the example program. So in this case, we have the program 1.c, and here we create a fork, and the program 1 creates a child process, and in this case, it executes the child process. If CPID, the return value of fork is 0, then this part will be the child process, else the parent process executes. And when it executes, it waits for the child process to finish, then it collects the wait status, and then it prints the child's process ID and prints the status and exits. Now an important point to note here is, in the child process, we have called an execl. So what happens is, we have now two processes in memory. One is the main process, which is nothing but the parent process. The other is the child process. Now in child process, we are replacing the virtual memory of the child process by a new memory, new virtual memory of program 2. Now in the memory, we have two separate virtual memories, and both the virtual memories are different now. Before, when we forked the child process, the virtual memory of the child was similar to the virtual memory of the parent, but in this case, the virtual memory of the child process is different from the parent's virtual memory because of execl. And this has a lot of use cases where the child process can execute its own set of instructions and return the status back to the parent process. Now let's open the program 2 code as well here. Here, this is the program 2 code. This is a very simple program where we print the process ID of the running program, and we print the arguments, command line arguments, and then sleep for 20 seconds in order to say that, in order to verify that the parent is waiting when the child is sleeping. Then the program 2 returns, and once it returns, this exit information will be collected in the parent. So let's compile both the programs separately and execute it so that we can have a clear picture on the combination of fork and exec. So now let's compile the program. GCC program 1.c minus o program 1. Let's compile the second program as well. Now let's run program 1, and let's have a look at the same time on the code as well. So when we run program 1, this program is run, and the program 1 forks a child process, and in the child process, the child process virtual memory is replaced by this program. Okay, so let's have a look into this. Now here, child, the parent is executing before wait, and child process ID is 18615. Now if you see here, the parent is waiting here at this point of time for the child to finish its execution, and child is executing a sleep of 20 seconds. Once the child finishes its execution, the wait function call is done in the parent process, and it comes out of the wait and prints the process ID of the child. So if you see here, this was the first parent process running, and it created a child 18615 with a process ID 18615. This is what we got here, parent executing before wait. So we got this here, parent executing before wait. Then we got before exec. This is from here, this one, where when the child process was created and it got the scheduling time and it executed this line. Now after that, it created an execl, and the new program was being loaded in the virtual memory of process child process. And if you note, this line is not printed, will not be seen here, because this program's virtual memory is being replaced by the new program. And when this is called, it begins its execution from the main of program 2, and we can see I have a new process called by execl will be printed here, and the PID is 18615. So if you note here, this programs 2 will be ran as a child process now, and this process ID and the process ID created by the parent is same, and these are the command line arguments passed from the from here, from the program 1, and the wait in the parent is done. So this will be this print will get only after the child sleeps for 20 seconds, and when it exits, it returns here, and the parent process executes and prints the following lines. So it prints the CPID, which is nothing but the child process ID, and also prints the status here. So status is 0 because it entered returned a 0 here. So this is the main use case of fork and exec together. Welcome. In this video session, we will discuss the relationship between the parent process and the child process and the open file descriptors. So let's say that the parent process has opened few files before the fork, and after opening few files, and now if the parent process forks a child process, then let's see what is the relationship between the child process and the parent process with respect to the file table. So as we have discussed earlier, whenever we do a fork or whenever a parent process does a fork, it creates a child process, and all the virtual memory of the parent process will be copied to the child process. So when a file is opened in a parent process, the parent process has a file descriptor table. So we had discussed this in the previous video lectures. So whenever a file is opened in a process, we have a file descriptor table which is per process basis. So every process will have its own file descriptor table, and we have a open file table which is a system wide. So whenever a file is opened, the file descriptor table is updated with the file descriptor of the file open, and it points to the open file table. So now in this case, here in the example, we have opened log.txt file, and the inode table contains the entry of the log.txt file, and as well, whenever we open the file log.txt in the process, we have a entry in the file descriptor table, and the file descriptor table points to the open file table, and the open file table contains the information of the open file, like what is the file offset and what are the flag status in which the file is open, and also the pointer to the inode table which points to the file actually. So this is the scenario before the fork. Now let's see what happens when the fork is called by the parent process. So this before fork, this the diagram what we see in the upper half is the same as this diagram. So this scenario is the before fork scenario, and after the fork, what happens is this file descriptor table is copied as it is in the child process also. So now the child process file descriptor table also contains the same open files that is being opened by the parent process. So now let's say a file is opened in the parent process and we have fd equal to some value and it points to a file from the open file table. Now after forking, the same will be duplicated. So there is a file descriptor table in the child process as well, and both the file descriptor points to the same open file table file. So going back to this diagram, so now we have one more process of the one more child process, and we have a file descriptor table in the child process as well, which points to the same open file table entry. So now whenever any changes in the parent process occurs, the same changes will be reflected in the child process as well. So let's say here when the parent process does a lseek and it has a file offset of 100 bytes. So this 100 bytes is also reflected in the child process as well. So in this scenario, if this is the parent process and it does a lseek on a common file, and now there is an offset of 100 bytes, let's say. So this offset of 100 bytes is also visible to the child process as well. So by forking, the child and parent shares a similar file descriptor table. In fact, it has the same copy of the file descriptor table as the parent process has in the child process, and both points to the same open file table. So now let's see a concept of, so going back to the slide. So now we can say that whenever a fork is performed, the child receives the duplicate of all the parents' file descriptor, and this also means that the file descriptor in the parent and the child refer to the same file descriptor. The open file descriptor contains current file offset that will be modified by the read, write, and lseek. So whenever any process does the modification of the file by read, write, or lseek, then the offset whatever is present in the open file table will be reflected in both the process. So as a result, the attributes of open file are shared between the child and the parent process. Now let's see a concept of the process table and process control block. So initially, when discussing, we had discussed that whenever a child process exits, then it has a entry in the process table. So this is the process table where in the process table we have a PID, that is nothing but the process ID of the process, and we have one more field called as process control block, and this process control block points to the data structure called as process control block. So this process control block is unique for a process. So every process has a process control block. So a process control block has few fields. So basically a process control block is a data structure, and this process control block is present for every process. And let's see the contents of the process control block. So the process control block is nothing but a data structure of each process, and there are many data members of the process control block. Let's have a look on a few of them. So we have something called as a program counter, the process number or the PID, the process state, the CPU registers, the process priority, the memory management information, and list of some open file process, and there are many other elements. So let's have a look why we need a process control block. So as we have discussed, Linux is a multiprocessing system. So there are many processes running on a Linux system. So whenever the CPU time of a process is finished, the scheduler will schedule the other process in the queue. When this behavior, the old process, when it resumes back, it needs to be resumed in the same state in which it was halted. So we have to save all the process state before the process leaves the CPU. The different states of the process are like at which instruction it was executing. So we need the program counter here, and then we need to save the process state, like what was the state of the process, whether it was in a running state or a wait state, log state. So we need to save the state of the process, and CPU registers will save all the current value of the CPU registers, so that when the process resumes, it reloads all the saved CPU registers back to the CPU register and then start performing the operation. And the process priority, like what was the previous stored process priority. And these are the different fields. There are many other fields, but we are just discussing few of the important fields. The process control block in Linux, it is referred by the data structure called as task underscore struct. So this represents the process control block in Linux. So this task struct is a huge data structure. So each process has each process or each thread in Linux has a task struct of its own.